Okay, we're going to look at another word problem here. So reading through this word problem, we're given some information about demand. So that's relating number of items to the price of the item. It's our lowercase p. Current daily production is given. It tells us how that's changing. And it asks us how something else is changing. So we've done several different kinds of word problems. Optimization problems, and then recently we've been working on related rates problems. So when you're given a word problem, one important thing is distinguishing which kind it is. So this is one where we're being told about how one thing is changing and asked about how something else is changing. And so that's what a related rates problem is about. It's not asking you to maximize or minimize something, but ask how these rates of change impact each other. Okay, so when you think about related rates problems, one of the things that you want to do is read through the problem and identify variables, right? So we have X for items, and I usually organize this information in a chart. Variables, and then the other thing in related rates problems is that you're given something about rates of change. All right, so variables, X is one of my variables, and so the relevant rate of change here is given in items per day. So this would be the rate of change of X. So that's with respect to time. So I have variables and rates, so we have something about X. Then other variables here would be price, and since our rate of change is with respect to time for that, we're also going to think about dp dt. And then it asks us here to find how revenue is changing. And so I don't have a letter in these equations for revenue, but we've talked before about how to construct a revenue function if you know price and quantity. So revenue is another variable that's described, and that's what we're being asked to find, is how dr dt, how the revenue is changing. So this is what we're being asked to find. All right, so I think it's helpful to just organize your information here, any variables that are mentioned, and then thinking about what the rates are, identify what it is that's being asked to find, and then also any other information that's given here. It tells us here that production is 500 items. So that's X, that's a specific value of X. It is changing. So it's not always 500, it's not constant, it is a variable, but that's what it is at this particular time. And then it tells us here that daily production is 500 items and is increasing by 20 items per day. So that's a rate of change. Since this is increasing, we know this is a positive rate of change. If they had said decreasing, I would use minus 20 here. So increasing by 20 items per day. I do have an equation for P, but there's no numerical value given here for P. It also doesn't ask me to find dp dt. So although that's a variable in the problem, if I'm not given information about it and I'm not being asked to find it, I just don't put anything in my chart for that. We might use it in other parts of the problem. And then R, not given any value for R either, but I am asked to find dr dt. So I think organizing this just at least helps you identify what information you're given and what you're being asked to find. Then the other thing that you want to do is you want to find an equation that relates your variables, and specifically the variable that you're being asked to find the rate of change for. So we know that revenue, we've been doing this kind of all semester long, revenue is price times quantity. So I could write that as P times X and have P in here, but eventually I want this to be all in terms of one variable, X. So instead of writing P times X, I'm going to write what P is equal to. So negative 0.05 X plus 1,500. So that's the price per item. It's a variable function times number of items. We've been doing revenue functions for a long time. All right, so this is my revenue function here. I've written it as R of X so that it's all one function of X. So let me just tidy this up here and make it R equals. So I'm going to take some derivatives. I'm going to go ahead and distribute through the X as well, just to make my derivatives a little simpler. I almost forgot my decimal point there. So negative 0.5 x squared plus 1500 x. Okay, and then I want to find how these things are changing with respect to time. So I'm going to differentiate both sides of this equation with respect to time. So d dt of both sides of the equation. So notice that my equation doesn't involve t, but I'm treating these things as functions of t. So this is where we use implicit differentiation, or really chain rule, kind of just two versions of the same thing, to think about what to write down here. So on the left side here, the derivative of r is 1, and then times the derivative of what's inside there. So we would just write dr dt. Maybe you don't think about the left side as chain rule, you just think about it as a rate of change. On the right-hand side, though, there is going to be some chain rule. I'm differentiating with respect to t, but this is x. X is a function of t. I know that from this information that was given here. So this is where we use chain rule. So I'm going to do the derivative of the outside function, which is the negative 0.5 times x squared. So bring down the exponent and subtract 1. I'll have negative 1x to the first power. And then times the derivative of what's inside there. So this is where you get that extra dx dt. This is implicit differentiation or chain rule that's happening here. So you don't have to write this 1 here. And then the next term here, derivative with respect to t of this term. So again, the derivative of this would be 1500, then times the derivative of x with respect to t. Okay, so then at that point, I'm ready to think about whether I can find what I'm being asked to find. So I like to label under my equation here what I'm going to put in. So this dr dt is what I'm supposed to find. And then looking at my chart here can help me think about what else is here. So I do have, it looks like, all the other values that I'll need to plug in. X equals 500, dx dt is 20, and dx dt is 20. So sometimes at this step we have to do a little bit of additional work to find some other values that maybe we need to plug in, depending on what the equation is. My advice is to not do that extra work until you get to this step, so you know whether you're even going to need to plug it in or not. All right, so dr dt, that's what I'm supposed to find, is negative x, so negative 500 times 20 plus 1500 times 20. So what do we get here? Negative 10,000 plus 30,000. So we get 20,000. All right, so that's the numerical part of our answer, but in these related rates problems, there should be units attached to that. And so that's when good notation and labeling of your work is helpful here. So dr dt is what I'm supposed to find. So the units on this would be the units of whatever r is, in this case revenue, per unit time. And this is a rate of change, so it tells us whether something is increasing or decreasing. It's a positive rate of change. So it tells us here that the revenue, R, is increasing by this much, 20,000, per 1 unit of whatever this variable is, t, time, in this case, days per day. Okay, so there is our numerical answer and then the interpretation of it. All right, try some more of these related rates problems.